In this movie, I'm going to talk about hidden Markov models. So I'll start by just looking at a brief example. So say I actually go out of my office and I look up to the sky and I see the sun shining. Let's say I do that each day of a week. So the first day the sun might be shining, but then the next day I might be unfortunate and see rain. And I live in Denmark, so I might have a couple of days with rain. Then I'm very lucky, get some sunshine. Then the next 2 days it's also raining. So this would be what we call our observables. This is something we observe. We observe the weather each day throughout the entire week. Now, the weather on each day might depend on something we don't observe. We call this hidden states. So it might be that on Monday it was high pressure, and this high pressure was actually what kind of caused influenced the sun shining. And we might have similar hidden states, maybe with low pressure the few next days, and we had like high pressure and low pressure. Then these are what we call hidden states. Great. So now a hidden Markov model would describe transition probabilities between the hidden states and emission probabilities between the hidden states and the observables. So we could make a diagram where maybe we have the hidden states here. We have the high pressure here and we have the low pressure here. And then the probability of going from high pressure to low pressure, we would like make an arrow like this. So then let's say the probability of going from high pressure to high pressure is say a quarter. Actually, let's just talk about if it is high pressure, then there's going to be some probability that we're going to see the sunshine and some probability of rain. Similarly, with low pressure, we're going to have some probability of sunshine and some probability of rain. So if the sun is shining with high pressure, maybe the probability of rain will be 3/4, and then the probability of sunshine will be 3/4, and the probability of rain might be a quarter. Then if we have low pressure, it might be that the probability of sunshine is a quarter and the probability of rain is 3/4. So then if we're in a high pressure state, the probability of going to low pressure state might be say 3/4, and if we're in a low pressure state, maybe it stays in a low pressure state. So this kind of would give us a lot of rain. Like very likely we have rain, and it's very likely we just stay in this state. So now we could actually look at what is the probability of kind of like these this kind of hidden states for these specific observables given this hidden Markov model. So you could look at what is the probability from the hidden state to the little state. With this is 3/4, and from this is also 3/4, and then from low pressure to high pressure is a quarter, and you could have like from high pressure to high pressure, that's also a quarter. High pressure to low pressure, that's 3/4, and then you could find what is the emission probabilities of the sun given when high pressure. Well, that's a quarter. Oh, that's actually 3/4. Sorry. And what is the probability of rain low? This is 3/4, and you could continue on and get all the probabilities, and then you could see how likely it is, given these observables, how likely is these hidden states as an explanation. So in this example, I had two different hidden states. So each of my hidden states were like taken from the set of high pressure and low pressure. So I might generalize this and say you can have k hidden states, and instead of having 7 observables, I might have n observables and corresponding n hidden states. So then we could write the hidden Markov model in a more general kind of sense, like z1, z2. So this is like the first hidden state, which transitions to the second hidden state, and this just keeps on going until we reach the nth hidden state. So each of these will take a value. This could be high pressure, low pressure, but now we generalized it so it could take one of k values instead of one of two values. And then in the kth, the nth guy, we would have like this could emit the first like some symbol xi, x2, all the way up to xn. So then in the general case, we might also say, well, we'll have, instead of just having sunshine and rain, we'll have maybe an entire alphabet of different things we could emit. So this will be, in the case above, this would have been like just sunshine and rain, but this might have been any arbitrary alphabet. So if we were modeling DNA, this would have been A, C, G, and T. But this could also have been anything larger. Great. So in the previous movie, I talked about dependency models, and in dependency models, we learned how to write up the joint probability of such a guy here. So the probability of z1 through zn, x1, xn is, well, we actually looked at it in the previous movie, but let's do it again. So this guy doesn't depend on anything, so we just write the probability of z1, and then we notice that z2 depends on c1, and c3 depends on c2, and so forth. So we can actually write all the transitions here as a product of I is 2 to capital N. Sorry, this has to be a capital N, capital N, capital N. And then the probability of zi given zi minus 1. And then we need to consider the emission probabilities. So this would be product from 1 to n, and then the probability of emitting x1 given in state zi. Okay. So these guys have some names. This is the initial probabilities. Just write init for initial probabilities. This is the probability of the first state. I didn't really consider that up here in the first example. So this is the probability that you might start in high pressure at the as the first hidden state. Then we have the probability of transitioning from zi to ending in zi given zi minus 1. So this is what we call the transition probabilities. And then in the last guy we have, well, given I'm in zi, what is the probability of emitting xi? So this could be like, if I'm in low pressure, what is the probability of emitting rain? Well, this is the emission probabilities. Great. So if we look at this diagram up here, it actually only has the emission probabilities, these are these guys, and the transition probabilities, which are all the arrows. So we didn't really have the initial probabilities in this guy. So when we code this, we say the parameters of our hidden Markov model, theta is the initial probabilities, and we'll denote this pi, and then it'll be the transition probabilities, we'll denote this a, and then the emission probabilities will note phi. So this will be a k-dimensional vector. We'll have one probability for each possible hidden state. So if this was hidden at low pressure only, we'd have like a probability of starting in high pressure, and so this high-low pressure only, we would have a probability of starting at high pressure and a probability of starting at low pressure. And if A was, then A would be a k times k matrix. So you can kind of think of the ijth guy would be the probability of being in the ith hidden state and transitioning to the jth state. So this is kind of like not that formal notation here. So what would phi be? Well, phi would then be the let's do it like this. Maybe it got a bit too long here. So this would be a k times alphabet size. So given I'm in, so then if we look at the ijth guy, maybe the ijth guy, then it's the probability of emitting the jth symbol in state I. So I mean, you can think of it as being in some hidden state, and then what is the probability of emitting something. Great. So now I just want to look a bit at the coding exercises. So if you're taking this course at Aarhus University, you will be doing coding exercises. And in here, we represent the initial probabilities. This is this vector. And the transition probabilities, so this would be pi. And the transition probabilities are represented here. This would be A. And then we have the emission probabilities here. So I drew over the emission probabilities as this rectangular guy. In this case, it's actually not like that, because you have more. In this, we have 7 hidden states: 1, 2, 3, 4, 5, 6, 7, and we only have 4 characters. We have an alphabet of size 4 because we are modeling DNA. So I just wanted to show you this, and then given these things, we can actually compute the probability of an observation and a corresponding set of hidden states, a corresponding explanation of these. So I'll just briefly see if I can find the code here, and let's see. So this is the code, the joint probability. So the model here encodes the emission probabilities, the initial probabilities, and the transition probabilities. So we'll say P is the probabilities, and then we want to return on given x and z, the probability of this pair. So we'll say P is the initial probability of starting in the corresponding state. So maybe if I just put this over a bit, this will correspond to the probability of being in the first state that we are given in the z. So this would be, in this case, this would be an H, like high pressure. And then we multiply this by the probability of observing the first observable given we're in this particular hidden state. So this would be, what is the probability of starting in high pressure, and what is the probability of emitting sunshine if you're in high pressure. Great. So that this will be like the probability of this guy, or up here, and then we'll loop for the through all the observables, and we'll multiply kind of the same thing, but with the emission probability of the emitting the ith symbol given when the ith state, and then the transition probability is also for going from state zi minus 1 to zi. Great. And then we'll return the probability in the end. So this is just an example, and it might not make that much sense to you if I run this. If you do the exercises, then this is the answer you should